Welcome to Dunwoody Mechanical Engineering. This is for MENG4211 HVAC. We'll be walking through a couple of problems from Chapter 16 in the Threlkeld, Kuehn, and Ramsey book. Let me swap this over. So we're going to be using some Excel here. I've got an Excel workbook set up. So far I just put the problem number 16.1 and I've given it a name up here. I'll type out the problem description up here so you can see what we're doing. So we're going to use the transfer function method. This mic is kind of in a bad place. There we go. Slide it over. Use the transfer function method to compute the instantaneous cooling load for the wall in problem 15.9 with medium construction, 370 kilogram per meter squared, and high air circulation. If we look back at that problem, we see that this is a number W4 wall. It is west facing and light colored. I think that's it. Oh, and then we also had TI is 26 degrees Celsius. So that was given in that other problem from 15.9. So if we look back at our transfer function method, we have equation. So the transfer function method, this is going to be equation 16.2, and this has the nu naught, nu 1, and omega 1, and it has an IHG multiplied by IHG ICL from a previous time period. So we're looking at the current heat gain and then some decaying factor of the previous tau minus, and I'll just call delta tau, if that makes sense. So we had some of that in there. So then we need the IHG for that equation from equation 1547. I don't have all of that out here, but that has those summations of Bn times solar air temperature minus summation Dn IHG minus Ti times summation Cn. So we'll look those up in a minute. So we need the solar air temperature. That's given in table 15.3, and those other equations or figures are given in I think that's 15.8 if I'm not mistaken. I think these are table 15.8. We'll look that up as we go. So hopefully that makes a little sense. So we're going to start with solar air temperatures for each time of day. Then we're going to calculate the instantaneous heat gain, and then we're going to use that in the transfer function method with those nu 1 and nu 0 and omega 1 to find the instantaneous cooling load as a function of time. So as we go through, I'm going to take in here, let's take that table 15.8. I believe that's what it is. So we're going to need N, we're going to have B, we're going to have D, Cn. Don't know if we need U. I'll grab it from there. Delta and lambda. So if I go back through table 15.8, flipping over in my book here. So 15.8, what do we have for these guys? There we are. So this is wall construction for W4. It's the fourth one down. So B, so N, we're going to go from 0 to 5. 0, 1, 2, 3, 4, 5. So B, we have 0.00009, then we have 0.01125, 0.04635, 0.02 654.00249 and 0.00003. Alright. And then for D, it starts in 1, so I'm going to put that gap in there, minus 1.5166, 0.64261, minus 0.08382, 0.00289, and negative 0.00001. Alright. And then for a sum of Cn, there's just one of those, so I'm just going to fill that in here. That is 0.086751. I'll grab the U value while we're here. I don't know if I need it. 1.9235, and delta is 7.3. Lambda is 0.33. All right, and we're working in SI, right? We have this in Celsius. These guys are in watts per meter squared C, along with B and CN, sorry. So we're good to go with those. So that's helpful for us that we don't need those. I'm just going to highlight these here to show that these are inputs to other things. I don't know if we'll need all of them, but I'll just grab those. Those came from this table 15.8. And then, so we got 15.8. We need the solar air temperature. I'll grab that in a minute. But then from table, let's see, table 15.3 has that. Oh, those other nu and W will come from table 16.2. So we have nu 0, nu 1, and omega 1. So this is from chapter 16 now. So a little bit of back and forth in the book. Flip, flip, flip. That's a little too far. Alright. So we have, this depends on our airflow, and we said this was a high circulation rate, and this was the mass was 370. So if we're looking in the book here, I don't know if you can see it, I'll try to hold it up, flip it over to the other screen. So looking in this book, right, so we're going to go for the heavy weight construction and the high circulation, or the medium weight construction, right? So there's, looking in the table, I see kind of in the middle here is 370, and then I'm going to go down to the high circulation rate. So I'm going to flip back to the spreadsheet. So for that construction for heavy, this is the omega 1 is from here. So omega 1 is negative 0.93, and 16.2 has our coefficients here for nu 0 and nu 1. So we are doing through exterior walls. Room construction is medium. So nu 0 is 0.681. And then in here we have 1 equals 1. So this is plus omega 1. So I'm going to grab that. Minus nu 0. Yes, so there we have that, and I'm going to put these guys here, right? So that was 16.2, this was table 16.1. Alright, so I think we're close. So I've got those values, so I'm going to use these to calculate TETD. So this is for, let's merge that to include that here. And then these guys are for, that's not for TETD, what is that for? That's for IHG, and this is for our ICL. So we're going to use these guys for ICL, we're going to need this for IHG, we'll need both of them to calculate ICL. Alright, so now we're getting close. Alright, so we need the solar air temperature, that's the other thing that we yet need. So I'm going to flip back in table 15. Let's see, where are we at? I think it's 15.8 if I'm not mistaken. That's 15.6, too far. Here's 15.8. So in table 15.8 we have, oh, that was where we got those values. We need the solar air temperatures. That's 15.3, sorry. Solar air temperatures. So here's flip back to the other screen here. So 15.3, probably covering that up, sorry, going the wrong way. So this is the solar air temperature. We have light colored wall. Right, it said that I think in the problem 15 description. And then we also need to look at the west facing, right? So we had the west facing, light colored, and we have this kind of trailing average business going on. So I'm going to start in solar time down here, solar air temp, and I'll put in TD. I think I'll need that along the way. IHG is in here, ICL per A, day 1, and I don't know if this will be smart enough. I'm going to see if I'll, oh, there we go, look at that. So we'll copy this over a few days worth. So I'm going to start a few hours earlier. So this is in hours, this is in degrees C. Nope, that's not degrees. This is in degrees C. This is in watts per meter squared, and this is in watts per meter squared. That's going to be the same. Is that going to do something? Oh, it's going to do something wacky. Alright, so I've got my units in there, and again we need kind of the trailing values. So I'm going to start 17, like 5 o'clock the day before. I might not need that much time, but I'm going to go from there. 21, 22, 23, 24. I'll call this 24, and then I'll do 1, 2. Scroll that down to 24. Alright, fantastic. And I'll just grab those last values when we come back through. So now I'm just transcribing the table for west facing 1 o'clock. We're at 24.4, 24.4, 23.8, 23.3, 23.3, 23.8. So I should be at 6 o'clock. Fantastic. 25.5, 27.2, 29.4, 31.6, 33.8, 36.1. So that should be 12 o'clock. Yes. 43.3, 49.4, 53.8, 55, 52.7, 45.5. So that should be 1800. Fantastic. 30.5, 29.4, 28.3, 27.2, 26.1, 25. And then I was going to grab these last few. Those are the same values earlier. So we'll put those in. There we go. So those came from, this came from table 15.3. Alright, so we've got that bit. Now we need to do the IHG is the sum of those guys. So IHG is a function of time. So I'm going to start with the 1 o'clock hour. I think I can do it without TET. So we'll see what I have here. So we're going to have... Alright, we're restarting or recontinuing this problem 16.1 from HVAC. So we're just review, we're doing the transfer function method. So this is problem 16.1. It's very similar to what we'll do in 16.3. That's just redoing an example. So looking at this, we've got our solar air temperature. Now we're going to do the instantaneous heat gain. So this is where we're going to be using the B's and D's and Cn here. So this equals the sum of our solar air temperature times, sorry, not that guy, times this, comma, this times that, comma, this times that, F4, comma, this times that, F4, and this times that, comma, this times that, F4. Okay, so we have that. So that's the first term of that internal heat gain. And then the next term is minus, got double minus the sum of our D's times our previous, D's times our previous flows here. So we're going to have this F4 times our previous heat gain, which is nothing right now, comma, this F4 times previous of that, comma, this F4 times that, comma, this F4 times that, comma, F4 times that, and then we take off TI, which is this guy up here, times the sum of CN, this guy. Alright, I think we got all of that in there, and I will want to, yes, so that should get us our heat gain. Fantastic. So we'll fill that through. Is that going to go through? There we go. And now you're looking, so we have these times now, the heat gains from these previous times, so I'm going to copy these, paste them special up here, so right click, paste the values, so that will update this first value. So before we ended up with 18.6 at the bottom, now we're at 20, so I'm going to copy that again until we get to a steady state here. So now we got 20.31, so we're getting closer. Now we're at 20.47, so just do this a couple times to get it. Now we're at 20.476, and down here we're at 20.49, so a couple more. Getting there. I'll do it probably 2 more times. 4928, 49268, so we're getting close. So that's pretty darn close there. Alright, so we got our internal heat gain, or instantaneous heat gain, sorry, not internal heat gain. Now, last bit, finding that ICL. So this is where we this new 1, new 0, new 1, new omega 1 comes in. So we're going to plug in our new 0. So I'm going to start here, equals new 0 times F4. F4 times our internal heat gain, instantaneous heat gain times that guy. And I'm going to put a column lock on that guy. And then we're going to add to that new 1 F4 times our previous heat gain. And I'm going to put a lock on the D column on that guy. And then we will, so we've got those two, and then we minus omega 1 F4 times our previous ICL times this guy. So there's that, fill that down. So there's that bit. And so I'm going to grab these last few here, copy those. I grabbed 18, so I'll paste those special. Now I'm going to grab these, copy that across, and change a little bit. Actually, I'm just going to do equals 18. So I'm just going to carry those through. Fantastic. So I'm going to grab these guys, and now I'm just going to copy those over. So we have this for 1 day, and I'm going to see how it evens out. So 619, 702, 71, 72. It's looking close. This might be steady state here. Yeah, it's looking pretty steady state, not quite, but pretty darn close. So we'd maybe have that as our values over here. So it took us 10 days. There's our final values there. So I would take, these guys would be my final values for instantaneous heat gain as instantaneous cooling load per area for that west facing wall throughout the day. So we're seeing that damping coming through, right? Our instantaneous heat gain was over here. Our cooling load, we're seeing damping out on that a little bit. So like here's 13, a little less. So what do we have? A peak 24 versus 20. So we're seeing that damping. So just big picture where we go, we had started off with our solar air temperature. We plug that in to find our instantaneous heat gain, and then we use that instantaneous heat gain with the nu and omega to find our instantaneous cooling load, the part that actually hits our heating system at that point. So you can repeat exercise for 16.3, which is one of the homework problems. We'll repeat exercise 16, I think it's 16.1 or 16.2, with a high airflow condition.